So my name is Shankara Pailoor, and today I'll be presenting MoonShine, optimizing OS fuzzer seed selection with trace distillation. So this is joint work with Andrew Ade and Professor Suman Jana from Columbia University. So let's get started. As you all know, security vulnerabilities in the OS are particularly dangerous as they can be used by attackers to completely compromise an affected system. OS fuzzing is a popular technique for automatically finding these vulnerabilities, and it's most often applied to the system call interface. This is for two main reasons. First, system calls can be invoked by unprivileged user programs, so any bug in the system call implementation could lead to a serious security vulnerability, like a privilege escalation or information leak. Two, the system call interface as a whole exercises a large and diverse portion of the kernel logic. So any bug in the kernel can probably be triggered through the system call interface. Now I'll provide a brief overview of OS fuzzing. So OS fuzzers usually start with a collection of synthetic seed programs, which are just sequences of system calls. These programs are then run on the target OS to find bugs. The fuzzer will then iteratively mutate and generate new programs in either a black box manner or by using some sort of feedback like code coverage. However, the most important point here is that in order for these system calls to actually test the core kernel logic, they oftentimes require some pre-existing kernel state. And the only way this kernel state can be set up is by other system calls. And in particular, in order for that state to be set up properly, these system calls must be executed in a particular order. We refer to these as dependencies. And existing OS fuzzers rely on thousands of hard-coded rules to properly set up these dependencies, which requires significant manual effort and is hard to scale. Our work focuses on this aspect of OS fuzzing. In the next few slides, I'll talk in more detail as to why OS fuzzers use these manual rules and why it's hard to scale. And afterwards, I'll show how our work, MoonShine, can improve the performance of OS fuzzers by generating seeds from system call traces of real programs. So as you know, the goal of the OS fuzzer is to find as many bugs as possible, but the more code the fuzzer can test, the more bugs it'll find. But before it can test the deeper kernel logic, it must be able to generate system calls that can bypass the shallow error handling regions. But the fuzzer cannot do this if it just randomly generates these system calls and their arguments. And to see why, let's go over a simple example of what is required to generate even a write system call. So here's the system call definition, and let's start with the first argument. So even though it's an int type, we all know that this value must correspond to a file descriptor that's in an open state with write permissions, and that this value must be produced by another system call like open. So as you can imagine, if the fuzzer just randomly generates these values, it's very unlikely that it will generate a valid system call, let alone the required open. The same is true for the second argument buff, which has to be a valid user pointer. But what's interesting here is that both buff and the third argument count are actually dependent on each other, since the entire memory region between buff and buff plus count has to be valid user memory. So if these arguments are generated independently, then that will greatly increase the chances that the call will fail. Therefore, in order to generate these valid system calls, OS fuzzers need to be able to track and maintain system call dependencies. So how do they actually do this? They do this by using templates with thousands of hard-coded rules. And like I said before, these aren't just simple rules to encode, but often require some significant manual effort. And to get a sense of the level of detail, let's take a look at an example template from syscaller, a state-of-the-art OS fuzzer for the Linux kernel. So here's the same system call definition for write, but just in the syscaller templates. And the first difference we should note is that the file descriptor is its own type, which has been marked as a resource, and I'll call this a semantic type. Open returns a file descriptor, and write takes the file descriptor as its first argument. So with this information, the fuzzer knows that the first argument of write must be produced by another system call, like open. The same is true for the second argument buff, which has to be a valid user pointer. Same is true for the second argument buff, which is of a type buffer, so it'll always be a valid user pointer. But this dependency between count and buff is now explicitly encoded in the templates, since count is now always set to be the length of the buffer. So with this information, it's easy to see that a fuzzer will be able to much more easily generate valid system calls. But unfortunately, it's hard to apply this level of detail to the entire system call interface, which consists of hundreds and hundreds of system calls, some of which have thousands of variants, like ioctl. And moreover, whenever system calls get added or calls get enhanced, these templates must be updated so that the fuzzer can trigger those paths. So it's not just a one-time cost, but it's an ongoing manual effort. So with this in mind, how can we do better? We can do better by generating seeds from system call traces of real programs. And real programs are interesting because they are required to maintain these dependencies in order to just function correctly. And if we can gather a large collection of traces from a diverse set of existing programs, we will find some interesting sequences of calls that are hard for these fuzzers to generate with just their manual rules. But we need to be careful because real program traces can be arbitrarily large, and if we use them directly as seeds, we'll significantly slow down the fuzzer's performance. But that's where MoonShine comes in. MoonShine takes these traces as input and puts them through a distillation process, which produces a small set of compact and diverse seeds that achieve the same functionality as the original set at a fraction of the size. And we refer to this process as trace distillation. But before I describe how MoonShine works, I'd like to briefly go over why we can't use existing seed selection algorithms to perform this trace distillation. So most of these strategies are some variations of this min-set algorithm. Min-set takes a large collection of inputs and then uses a greedy heuristic to find the smallest subset that achieves the same code coverage on the target application as the original set. This subset is then directly used as seeds for the fuzzer. So how could we use min-set to do trace distillation? There are two obvious possibilities. So we could use it to get a small subset of the traces, but that's not good enough because even if we take a small subset of the traces could still be arbitrarily large. And a small set of very large traces will slow down the fuzzer performance. We could also use it to get a small subset of the overall calls, and this will be much more compact. But if we do not include their dependencies, then these calls will fail, and they're unlikely to provide any benefit to the OS fuzzer. But there are tools like AFLT-min, which are designed to minimize individual inputs to the fuzzer. And they work by first arbitrarily removing some amount of data from the input, so in this case, some amount of system calls. And then they just check to make sure that this removal didn't result in any loss in coverage. But this doesn't really work with system call traces because this tool doesn't have any understanding of the complex dependencies between system calls. So when it just removes an arbitrary amount of calls, it could easily be removing one of the interesting ones or their dependencies. So in practice, something like tmin will have to exhaustively go through sequences of calls before it finds a minimal one, which can make it prohibitively slow on even moderately sized traces. So with this in mind, there are two challenges we need to address in order to perform efficient trace distillation. We need to be able to reliably minimize the trace size while also tracking the system call dependencies so that their behavior is preserved. But before proceeding, I'd like to describe in more detail why we choose to minimize the traces. And in our experiments with syscaller, which is our target OS fuzzer, we found that when we used seed programs that had more and more calls, the fuzzer's performance got worse. The fuzzer's performance got worse. By performance, I mean the number of mutations, program executions, as well as programs generated. And we ultimately found that when we used these traces directly as seeds, syscaller was unable to find any new bugs. And so the graph on the right is just one example of this impact. So the x-axis shows the time spent fuzzing, and the y-axis is the total number of mutations that syscaller performed. And this graph shows the performance of syscaller when using different seeds of varying sizes. And as you can see, when using the larger and larger seeds, the ones that had more calls per program, syscaller performed noticeably fewer mutations. But the programs we're talking about are really between 100 to 1,000 calls per program. But if we look at some of these larger real programs like Chromium, even in a 10-second trace, they can produce 500,000 calls, which is far too large for direct use. But fortunately, the number of calls within a trace that contribute new coverage is just a small fraction of the total number of calls. And we found that even for these relatively compact small programs like LS, only about 1/10 of the calls actually contributed new coverage. So our initial strategy will be to keep the calls that contribute the most coverage using a greedy heuristic. And then also include their dependencies so that their behavior remains unchanged. So MoonShine tracks these two different classes of dependencies, explicit and implicit dependencies. And these are the dominant forms, dominant ones in our traces. So broadly speaking, you can think of an explicit dependency as a case where this shared state is passed through the system call arguments. And an implicit dependency is a case where a system call affects the behavior of another call by modifying some shared kernel state. So now I'll provide more precise definitions of each, starting with the explicit dependencies. So we say a call A is explicitly dependent on call B if B produces a result used by A. So in the example below, we would say that write is explicitly dependent on open because open produces a file descriptor of value 3 used in the first argument of write. Now we say a call A is implicitly dependent on call B if B affects the execution of A by modifying some shared kernel data structure. So this is a bit more complicated, but I think a good example is between the msync and mlocall system calls. So in this case, we would say that msync is implicitly dependent on mlocall because mlocall affects the execution of msync by modifying all the VM flags fields of every VMA struct in the calling process. And then in msync's execution, it checks to see if this field has been marked as locked, and if it has, it will set error to ebusy. So now I'll go on to describe how MoonShine actually tracks these dependencies, starting with the explicit dependencies. So it does this by statically analyzing the trace. So as it parses each call, it identifies all the values that were returned along with their corresponding types. And so this type could either be a data type, like an int, pointer, or string, or a semantic type, like a file descriptor. These type value pairs are then inserted into a hash map, which maps the pair to all the calls which produce that same pair. We call this map a return cache. Then for every argument that is not modified during the execution, we construct its type value pair and check to see if it's in the return cache. If it is, we add all the calls which produce the pair as explicit dependencies. MoonShine tracks the implicit dependencies by using a lightweight static analysis on the target OS. So it performs this analysis at the system call definition, and then it proceeds to walk the kernel AST while checking for two conditions. So the first condition is if a call C uses some shared variable V inside of a conditional expression, then it will mark C as read dependent on V. And if a call C writes to a shared variable V, it will mark C as write dependent on V. And this shared variable could be a global or a process-wide structure. So with this information, MoonShine will say if a call A is implicitly dependent on call B by taking the intersection of A's read dependencies and B's write dependencies. And if this intersection is non-empty, it will say that A is implicitly dependent on B. The intuition here is that if a call A uses a shared variable V inside of a conditional, then its control flow could depend on the value inside of that variable. So any other system call that modifies that variable could affect A's control flow. So we note that both of these methods for tracking the dependencies will have false positives and false negatives. But as we'll show later, MoonShine is still able to effectively distill these traces while preserving most of the dependencies. So let's put this all together and see how MoonShine will distill the trace on the left. So recall that it starts by identifying the calls that contribute the most new coverage. So let's assume that is these three. So it'll add them to the distilled trace. It will then add all their dependencies, starting with the explicit dependencies. So it first observes that mmap is explicitly dependent on open because of this shared file descriptor. So it adds open to the distilled trace. It then sees that msync is explicitly dependent on mmap because of this shared virtual address. But they are already in our distilled trace, so it doesn't do anything. Since there are no more explicit dependencies, it moves on to the implicit ones. And the only one it can find is between msync and mlocall, like I described before. So it'll add mlocall to the distilled trace, but since there are no more dependencies to add, it'll mark the trace as distilled. So our current implementation of MoonShine only generates seeds for syscaller, which is a Linux kernel fuzzer. But we chose syscaller because it has a very rich set of templates with a number of sophisticated manual rules. And it's also a evolutionary fuzzer, so we know it'll benefit from well-chosen seeds. We gather traces using strace, but we've also extended it to capture per system call code coverage using kcov. We track implicit dependencies using SMATch, a static analysis framework for the Linux kernel. We identify read dependencies using a condition hook and write dependencies using a unary op and assignment hooks. Most of our implementation is in Go with a little bit in C. So now I'd like to share some results from our evaluation of MoonShine. So our setup was we first gathered about 3,200 traces from 4 seed sources: the glibc test suite, Linux kernel self-test, Linux testing project, LTP, and the OpenPOSIX test suite. All our results are using seeds generated from these traces. So our first result is that MoonShine was able to find 17 new vulnerabilities in the Linux kernel that syscaller could not with its manual rules alone. And a number of these bugs had significant impact and could be used for denial of service or privilege escalation. Most of these bugs were also in the core subsystems of the kernel, like the core networking and VFS, which are among the most widely used and well-tested parts. But most importantly, all of these bugs could only be found when using distilled seeds. And in particular, 10 out of the 17 could only be found when using seeds that maintained implicit and explicit dependencies. Code coverage is another important feature to evaluate the performance of fuzzers. So we measured the impact of MoonShine on syscaller's code coverage in a 24-hour fuzzing period. So the graph on the right shows our results. The x-axis is the time spent fuzzing, and the y-axis indicates the total coverage. And we measured 3 cases. We measured syscaller using just its manual rules. We measured the case when it used seeds that tracked implicit and explicit dependencies, which we say is MoonShine I+E. And lastly, the case when it just used seeds that tracked explicit dependencies, MoonShine E. So we found that just tracking the explicit dependencies resulted in a 9.7% code coverage increase, edge coverage increase. And by tracking both explicit and implicit, we were able to increase that to 13.1. And finally, we find that MoonShine is able to effectively address its challenges. In particular, our collection of traces had 2.9 million total calls, but after distillation, this number went down to just 16,400, which is 176 times smaller. But most importantly, these distilled seeds were still able to achieve 86% of the code coverage from our original set of traces. Now I'd like to share one of the vulnerabilities that MoonShine discovered. So this was a pretty serious bug in the iNotify subsystem, and it is due to a race condition between the kernel function, iNotify handle event, and the system call rename. So the condition for the bug is as follows. iNotify handle event starts running on CPU 1, and it begins by allocating kernel memory for this event struct. The amount it allocates is based on the current length of the file name. And then after this, but in parallel, another thread will call rename that changes this file name to something which is much longer. But iNotify handle event doesn't expect this rename, so it will eventually just call stir copy to copy the file name into the event. But if this executes after the rename, then it will result in a buffer overflow, and this can be used for a privilege escalation attack. We note that this bug was in the kernel for almost 2 years and went unnoticed until MoonShine discovered it. It was also in the core VFS subsystem, so it was in every Linux distribution and Android. So how did MoonShine actually help find this bug? So this is the program which caused the bug, and it is a distilled seed that MoonShine generated from one of our LTP traces. The calls responsible for the bug are the iNotify add watch, close, and rename. The actual race condition was between close and rename, and syscaller induced this bug by executing these calls in separate threads, which it will often do to find racy bugs. However, the program on its own didn't trigger the bug, but it required syscaller to mutate this short toString into something which was much longer. And we never observed this bug when we used the undistilled trace, because it was unlikely that syscaller could ever actually make this mutation. So in conclusion, existing state-of-the-art OS fuzzers rely heavily on thousands of hard-coded rules to track system call dependencies, and this requires significant manual effort and is hard to scale. But we have designed, implemented, and evaluated MoonShine, a framework that automatically generates compact and diverse seeds from traces of real programs. And it can automatically track and maintain a system called dependencies using lightweight static analysis. And the seeds generated by MoonShine resulted in the discovery of 17 new vulnerabilities in the Linux kernel. And with that, we've also released MoonShine as an open source tool here, and it's getting integrated into Syscaller. And so with that, I'd be happy to take your questions now or offline.
Let's thank our speaker.
I'm Yang Zhengbai from ARM. I have two questions. The first one is like, can we use this, the MoonShine to test the performance bugs in the kernel?
I have not considered that. So off the top of my head, I do not know. So, well, I guess in general, I know that there's been some work in terms of fuzzing to find performance bugs. So perhaps it depends. I think your seed selection strategy would have to be such that you know that the fuzzer will mutate it in a way that will result in longer executions. But off the top of my head, I don't know. Sorry.
Okay. The second question is like, do you plan to support a perf trace instead of an S trace? The statistical sampling trace, so the perf trace, Linux perf tools.
Oh, no, we don't support that now, but that's something we can add.
Okay, thanks.
Hi, Ardon Amirsani, UC Irvine. Very nice work. I had a question about your slide 27, where you were showing the code coverage. And I see that it's a 20-hour experiment approximately. So
it's 24 hours.
So I was wondering what happens after. Does it saturate at some point? Because it seems like the coverage keeps
I think both, yeah. So yes, both of the code coverage, both of these metrics do saturate at that 24-hour limit. Actually, they saturate a lot earlier, but they seem to both grow at the same rate after 24 hours. So it seems like what our seeds are doing are providing Syscaller access to new parts of the kernel, but they're still getting stuck at that particular layer.
Right, so you're saying at 24 hours it saturates. After that it's not increasing, or it's still increasing?
It's still increasing, but slower.
Slower.
I mean, it could eventually find some branch and evaluate it true and then go much deeper. Mm-hmm. So.
Okay.
I'm Jamie Davis from Virginia Tech. It seems, if I understand correctly, like you need access to the operating system source code in order to do your analysis. Is that correct? And if so, what if you didn't have access to the OS code?
Yeah, that's a good question. So currently it does depend on, it's a source code based technique. But I think there are two possible options. One, you could do a dynamic method, maybe at the hypervisor level, to track these dependencies. But we have not gone in that direction yet. You could also maybe do a binary analysis, but I have not tried that either. So.
Thank you.
Let's thank our speaker again.